Okay, level 3 NCEA physicists, continue on with our nonlinear internal 3.1. Last lesson we looked at errors. This lesson we're looking at graphical techniques and basically data analysis. So the first thing you have to do is you have to tabulate your results. So in terms of this internal, the result table needs enough columns to handle all the data. The appropriate units are required for the variables, so SI units. The uncertainties of the variables have to be calculated for both the first and the second graph. Multiple readings are required both for the independent and dependent variable, and the average for the dependent variable is also required. So in terms of your manipulation of uncertainties and your processed data for the second graph, you also need to provide examples of how you have done that in the report, so I know what you've done. So in terms of graphing mathematical relationships, this is what we want for the second graph. We want a nice linear relationship where y is proportional to x, so we can take the gradient. But in order to do that, we need to first plot the first graph. So you're going to get a range of shapes which will determine how you're going to manipulate the second graph. So this is an example here of a y is proportional to x squared graph. Okay, it's an exponential graph, which means for the second graph, you do a plot of y against x squared to get a linear relationship. So in the second graph here, we've got a y is proportional to 1 over x, an inverse relationship. So to get a linear relationship from that, it would be a plot of y against 1 over x. This is the third type of graph you might see. It is a relationship where its y is proportional to the square root of x. So to get a linear relationship from that, you'd plot y against the square root of x. And finally, for graphical mathematical relationships, this is a 1 over x squared relationship. Okay, so to plot that, you would do a y versus 1 over x squared, and that should give you a straight line relationship. So in terms of the expectations for the graphs for this internal, for both graphs you need a title describing the two variables, which is relevant and descriptive, effectively descriptive enough. Both axes are labeled with the quantity and the appropriate SI unit. The appropriate scale is used, and it is equidistant and sufficiently large if you're doing hand plotting. The points are plotted as crosses. Anomalies are identified by a circle around them. Okay, and that's in both graphs, as you can see also on the image we have on the screen. If the graph is nonlinear, which is what you're going to get for the first graph, the data needs to be processed to create one. Okay, so that's going to be the processing of the data which we put in the table, and also to generate your second graph. And in both cases, you'll need a line of best fit. Okay, so for the first graph, that might be an appropriate curve. Okay, so for example, if you've got a y is proportional to x squared relationship, you need to do a exponential line of best fit to get the curve to fit your data. And in terms of the second graph, because it's linear, you also need to plot a line of maximum error and a line of minimum error, which we'll look at soon. And you've also got to incorporate error bars in both of your plots. So in terms of error bars and lines, the error bars from each point show the uncertainty from that point and the x and y direction. So for example, if you're doing force on the y-axis, then you need to show error bars of plus or 1 Newton for each of your values, if that indeed is the uncertainty for the force. Okay, so the error lines are basically plotted as the extreme values of the plus and minus values, the absolute uncertainty. And then for your second graph, you will need to also plot a maximum error line, which is essentially the steepest gradient from the error bars that you have generated, and a minimum error line, which is the shallowest gradient from the error bars you have generated. So you need 3 lines essentially for your second graph: a maximum error line, a minimum error line, and a line of best fit from your data. Okay, and the error line you will choose to work out the error in your intercept and gradient will be the one which is the largest difference from the gradient, or from your line of best fit, which you'll also have to calculate. So in terms of the gradient, it's going to be calculated by the change in the y variable divided by the change in the x variable. And if you're doing a hand plot, that'll be 2/3 the line of best fit. Okay, and the unit, which you will also require, will be essentially the unit of the y variable divided by the unit on the x variable. And to calculate the uncertainty of the gradient, it is essentially the absolute value of the gradient of the line of best fit minus the gradient of the line of error that you've chosen. Remember, it has to be the largest one. In terms of analysing the graph too, you also got to determine the error in the intercept value. Okay, so the intercept is essentially the y-intercept when x equals 0, and the line of best fit intercept is the y-intercept of the line of best fit, makes sense. And the unit of the intercept will be that of the unit of the y-axis, okay, the y variable. And the absolute uncertainty will be, again, the absolute value of the intercept of the line of best fit minus the intercept of the line of error. Okay, so you're going to actually have to work out the intercept of both of your error lines and determine which one is largest in order to work out the absolute uncertainty in your line of best fit. Okay, so you end up with an equation of y equals m plus or minus the absolute uncertainty in m multiplied by x plus the value for your line of best fit intercept plus or minus the absolute uncertainty in the line of best fit, or the intercept anyway. Okay, so that's pretty much all you have to do for the analysis of your graph and your data and crunching the numbers. And our next video, we'll be looking at how you're going to discuss and conclude your internal in order to get excellence.